Hello everyone, welcome back to NPTEL lectures on cycloaddition reactions. In the last 5 lectures, we have been talking mainly about 1,3 dipolar cycloaddition reactions, and today we also will continue to discuss a few more 1,3 dipolar cycloadditions, particularly the dipoles like Diazoalkanes, Nitrile Imines, Azomethine Imines, and Nitrile Ylides, how these dipoles are used in 1,3 dipolar cycloaddition reactions. First, let us start with diazoalkane. As we all know, one of the simplest diazoalkane is diazomethane. And if you look at the history of 1,3 dipolar cycloaddition reaction, the very first 1,3 dipolar cycloaddition reaction was reported way back in 1888. It is almost 150 years ago by Buchner, and it was between diazoacetic ester and dimethyl fumarate. So this is the reaction. As you can see here, this is the dimethyl fumarate, and this is the diazoacetic acid methyl ester. So when they heated these two, so they got this one pyrosol. We'll get back to the mechanism a little later. If you look at the history, as I said, this is the first 1,3 dipolar cycloaddition reported in the literature. If you carefully look at the mechanism as well as the transition state, so the transition state looks like it's not a polar transition state, so that obviously means the solvents will not have any major role, or in other words, polarity of the solvents will not have any major role. So for example, if you take diazoethane and then treat with this alkyne having an electron donating group at one end and electron withdrawing group at another end, so this can undergo immediately 1,3 dipolar cycloaddition to form this pyramidal ring. And now you can see there's a hydrogen here. This can undergo, in principle, 1,5 hydrogen shift to form this substituted pyrosols. Or in other words, if you choose the substrates properly or the dipolophiles properly, you can easily make several pyrosol derivatives using this 1,3 dipolar cycloaddition. Coming to the TGO and stereo selectivity of this dipolar cycloaddition, as we have seen already and then discussed, the 1,3 dipolar cycloaddition reaction is always highly stereo selective and PGO selective. So if you take this phenyl diazomethane and then do 1,3 dipolar cycloaddition with methyl dimethyl maleate, so since these two ester groups are cis to each other, and in the product too, you will see both of them are cis to each other. However, the phenyl group here, it can be either cis or trans to the ester. Okay, because it has equal opportunity. It can come either from the top face or from the bottom face. So that's why you get mostly 1:1 mixture of these two ester. And in this particular example, this double bond will behave like a dipolarified, and this is a symmetrical compound, and this upon treatment with this diazo compound, it can undergo a 3+2 cycloaddition to give this tricyclic compound. And as you can see here, the attack of this dipole is from the exophase of this bicyclic compound. So that's why you can see in the tricyclic compound, this dipole comes from the exophase. And coming to the PGO selectivity, and it comes as a result of the HOMO-LUMO interaction, and particularly the HOMO of the dipole and the LUMO of the dipolarified, they interact to get the 1,3 dipolar cycloaddition product. So normally when you do this reaction, what you get is the pyrozolene, and the pyrozolene is not the direct product. It goes via this initial 1,3 dipolar cycloaddition product, and followed by the migration of this hydrogen, you get the corresponding pyrosol. So this is the molecular orbital interaction. As you can see here, this is the HOMO of the dipole and this is the LUMO of the dipole of 5. This is the major interaction and that leads to this product. And if you take, for example, instead of hydrogen in methyl acrylate, if you have a methyl group at that position, then after the 1,3 dipolar cycloaddition reaction, there is no possibility of hydrogen migration. So you end up in getting delta 1 pyrazolene, whereas in the other case, when instead of methyl, if you have hydrogen, the hydrogen migration will take place to give the delta 2 pyrazolene. So that can be controlled by having an alkyl or aryl group at alpha position. And in this case, when you do a dipolar cycloaddition between this enamine and this ethyl diazoacetate, so it goes through this particular 1,3 dipolar cycloaddition product. So that is nothing but this compound. And here, what happens? After the reaction is over, then elimination of pyrovidine takes place to get the corresponding pyroxene. And if you have diazomethane, and if you have a diene ester, and the terminal double bond actually undergoes 1,3 dipolar cycloaddition with diazomethane to get this delta 1 pyrazolene derivative. And a similar example that we have already discussed, here we have ester, which is attached to diazo compound, and we have an electron donating diethyl amine group attached to the triple bond. This can undergo 1,3 dipolar cycloaddition to form this delta 1 pyrazolene, but this will further, as I said, can undergo 1,5 hydrogen shift to form the corresponding pyrazole. And in this particular case, what we have is the dimethyl and the diazo compound. And this can undergo the 1,3 dipolar cycloaddition to give this derivative. Here there is no possibility of 1,5 hydrogen or 1,3 hydrogen shift because you have a gem dimethyl group, so the migration is not possible. But one can use fluoride source to remove the trimethyl silane group. Once you do that, you get this product. Now this product again can undergo another 1,3 dipolar cycloaddition with this diazo compound. So that will give this bicyclic compound. Now you can see in both cases a stable leaving group, that is nitrogen, is possible. So when one of the nitrogen goes out, then you will get a double bond. Okay? Now the nitrogen goes out, first it will form a cyclopropane, and then cyclopropane will rearrange to the corresponding double bond. Okay? This all can be done by simply heating this dipole of 5 with excess diazo compound. Okay? And in between, of course, you have to add fluoride source to remove the TMS. Okay, so from now diazoalkane, now we will move to nitrile imines and how these nitrile imines are used in 1,3 dipolar cycloaddition. So the nitrile imines were, basically organic cyanides are called nitriles. So now if you attach any amine to that, and then you have a positive charge here, and now this N minus, NH will become N minus. So this is nitrile and this is imine. So that's why it is called nitrile imine. Okay. So this is usually prepared. Suppose if you have a hydrazone, okay, if you have a hydrazone with a leaving group here, you have hydrazone with a leaving group at alpha position. So then this lone pair, you can see on the nitrogen, can push this X out. It is almost like preparing nitrile oxide. You can recall how to prepare nitrile oxide, a similar method. So once you do that, you get this N plus and NH, or then this hydrogen can pick up to give the corresponding nitrile imine. So this nitrile imine can undergo 1,3-dipolar cycloaddition with alkenes, for example, with enamines of this kind. Then it can give a 1,3-dipolar cycloaddition product like this. And again, like the earlier example where, reaction between enamine and diazoalkane that led to the elimination of pyrrolidine. Here, the elimination of morpholine is possible, so that will lead to this substituted pyrazole. So the end product is pyrazole, and here the morpholine is lost after the 1,3-dipolar cycloaddition reaction. Okay, let us see very simple example where you can see this is benzonitrile and this is aniline. So now if you see the whole thing is called diphenyl nitrile imine. This is one phenyl, this is second phenyl, and then diphenyl nitrile imine. And this can undergo intermolecular 1,3-dipolar cycloaddition with cis-stilbene, and the same cis nature of stilbene is retained in the product. And if you treat with trans-stilbene, then the trans-stereochemistry is retained. As you know, the stereochemistry of stilbene, this is cis-stilbene, and this is trans-stilbene. Okay, whatever stereochemistry the diplurophile has, that can be easily retained in the 1,3-dipolar cycloaddition product. Again, as I said, this type of nitrile imines are generally made from such hydrozones. Okay, if you have alpha chloro hydrozones, then if you treat with bases like triethylamine, then the lone pair first, it will eliminate the chloride to generate triple bond with triple bond N, and then N having positive charge, and followed by removal of this hydrogen will give you nitrile imines. So once you have this imine, then one can do several 1,3-dipolar cycloaddition with various dipolarophiles. For example, if this is done with this alpha beta unsaturated ketone, here, interestingly, it has an aldehyde, it has a ketone, and more importantly, you can also see there is an oxygen which can use this lone pair. So it's like a push-pull system. And when this undergoes an 1,3-dipolar cycloaddition reaction, then you get this tricyclic compound. So if you analyze this particular product, this is nothing but beta keto aldehydes. The beta keto aldehydes can be easily removed. If you heat it, or if you do acidic treatment, then the beta keto aldehyde can be easily removed. One can also add base, nucleophilic bases like OH minus, then also you can easily remove. Here in this case, even water is sufficient, so water can act as a nucleophile, and when it does that, now you can see here the driving force is the formation of phenol as well as this aromatic. So these are the two driving forces how the aldehyde is easily eliminated in the reaction mixture. And if you take this dipolarophile, okay, and again the precursor for the nitrile imine, so when you treat with triethylamine, then you will get the diphenyl nitrile imine. So that will undergo 1,3-dipolar cycloaddition to give this product. Can you see in this dipolar cycloaddition reaction, the other component is eliminated. Okay, the other component which is attached to the styrene is eliminated. How does it happen? So first it forms the nitrile imine, then it undergoes a 1,3-dipolar cycloaddition to get this compound. As you know, normally if you have any group like pyrrolidine, morpholine, so that can be eliminated. Now you have this pyrazole, so this can undergo elimination, and when you use acid under that condition, you get your 1,3-dipolar cycloaddition product as well as the. So this is oxazole. There are many methods to make nitrile imines. For example, if you take the phenyl hydrazine and then treat with an aldehyde, okay, basically it should form first hydrazone. Then since you are doing this reaction with potassium bromide, so it can form the alpha bromo hydrazone that upon treatment with triethylamine can give this nitrile imine. Okay, so all this, you can do in 2 steps, but 1 part protocol to make this nitrile imines. So once you have this nitrile imine, and you can treat with various dipolar, and you can see here even oximes can be used as dipolar. Okay, so that means what you will get if you use oxime, you will get first you will get this intermediate. So now the loss of water will give you results. And if you use a ketone, okay, it is again, we can call it under broad category called heterodipolar cycloaddition reaction. Okay, so now you have a carbonyl group, and the keto group is having 2 electron withdrawing group attached to that. 2 ester groups are attached to that. So this carbonyl group now will act as a dipolar to get this. And one can also use diethyl azo dicarboxylate. So this is coming out from diethyl azo dicarboxylate. So the diethyl azo dicarboxylate here acts as the dipolar. So in principle, once you make nitrile imine in situ, one can easily carry out 1,3 dipolar cycloaddition with various dipolar. Okay, so now we will slowly move to the next dipole, which is azomethane imines. Azomethane imines. So this is called azomethane imines. So earlier example we saw, this is nitrile imines. So it is a triple bond here, and if it is double bond, okay, if it is double bond, then this is called azomethane imine. Okay, we also earlier discussed azomethane ylides. Okay, so instead of carbon, if it is nitrogen, this is azomethane imines. And azomethane imines are of 3 types, where you have the acyclic azomethane imines. These 2 examples are acyclic azomethane imines. The second example, you can see here there are 3 examples which I have shown here. In all these cases, the imine portion is part of the ring, or N minus is outside the ring. Okay, this is the second type of azomethane imines. Then the third type, where the N bond, in all the 3 cases, the N bond is inside the ring, whereas the N double bond C is outside the ring. So these are the 3 different types of azomethane imine, and let us see how these undergo 1,3 dipolar cycloaddition reaction. Before that, we'll see how these azomethane imines are made. It is very easy to make azomethane imines. What you have to do, you have to have hydrazine derivative, okay, NH2, and one side it should be protected with electron donating group, the other side it should be protected with electron withdrawing group. Why? Because when it is protected differently, the more nucleophilic nitrogen can form iminium ion with aldehyde, whereas the less nucleophilic one can lose the proton to form azomethane imine. So now if you look at this hydrogen derivative, one side the NH2 is protected as NHBN, whereas the other side it is protected as NHBZ. So now between these two NH, this NH is more nucleophilic, so this will undergo iminium ion formation spontaneously, and this hydrogen can be easily lost. So that is how this azomethane imine is formed directly in one step from alene. Once you have that, then this can undergo 1,3-dipolar cycloaddition with various alkynes and alkenes. For example, if it undergoes 1,3-dipolar cycloaddition with phenylacetylene in the presence of copper salt, one can easily get this 5-membered ring. Likewise, this example you see, this is NHMe, this is more nucleophilic, and this is NHCOMe, it is less nucleophilic. So obviously the iminium ion will form with NHMe, so that's why you get this azomethane imine. So once this is formed, then this can undergo various dipolar cycloaddition with the dipolar philes, and if it undergoes 1,3-dipolar cycloaddition with N-phenylmelamide, one will get this bicyclic compound. Very simple. And one can also think about intramolecular 1,3-dipolar cycloaddition if azomethane imine can be generated in situ, and also the substrate should have the dipolar phile. Okay, so now if you take this example, this is the dipolar phile. Okay, now you have this ketone, and this ketone, if you treat with acetyl hydrazine, okay, now between these two, as you know, this NH2 will immediately react with carbonyl group to form imine. Then internal proton transfer will take place to form iminium ion, and this N will become N minus. Okay, so what happens? The NH2 reacts with ketone to form this imine. From here, the NH goes here to the next nitrogen to form iminium. At the same time, it forms N minus. Once it forms this azomethane imine, then you have the double bond, which is part of the substrate. Then it can undergo an intramolecular 1,3-dipolar cycloaddition to form this compound. So the way I have drawn the 6-membered ring, chair-like transition shape, so that you can easily see how stereoselective this reaction could be. If you look at this example, so this is 3-methyl indole. The first step, this NH is being alkylated with this allyl bromide. Okay, and in the second step, the aldehyde is being introduced using Ilse-Meyer-Hawk reaction. Now, if you treat with phenylhydrazine, okay, so this NH2 will form imine, and followed by intramolecular proton transfer, one will get the corresponding azomethane imine, and that will undergo spontaneously intramolecular 1,3-dipolar cycloaddition to get this tetracyclic compound. So all this, if you look at from known 3-methyl indole in 3 steps. Okay, so then one can also make azomethane imine like this. This is, if you have a closer look at this compound, so this is nothing but a dihydroisoquinoline unit. Okay, and this azomethane imine can easily undergo 1,3-dipolar cycloaddition with alpha beta unsaturated esters like acrylonitrile to form this as the major form. Okay, so this is easily explainable because of the large HOMO coefficient of this nitrogen and large LUMO coefficient of the beta carbon of the dipolar phile. Okay, this is a dihydroisoquinoline, but here if you see, so this is the quinoline unit. Okay, the quinoline unit, and then you have the corresponding azomethane imine. Now you have an allene So now there are two double bonds, one and then two. Which one will undergo 1,3 dipolar cycloaddition? Obviously, this double bond will undergo 1,3 dipolar cycloaddition, and it can give both isomers, where you can see the hydrogen can be beta or hydrogen can be alpha. Okay. So aldenes are also good dipolar in 1,3 dipolar cycloaddition reaction. So this is very interesting example. You have an aldehyde and a leaving group, that is bromide. Now you treat with hydrazine, simple hydrazine. So what you get is you get this penethyl bromide, and the other side it forms hydrazone. Now the lone pair on the nitrogen of the imine will attack, and intramolecularly, so you get the corresponding 6-membered ring and NH minus, intramolecular proton transfer. Okay, now this can undergo 1,3 dipolar cycloaddition with phenyl methyl propionate and followed by hydrogen migration, you get this compound. Okay, and this is another classical example where titanium binolate. You have a binol, it's a chiral compound, and then titanium. So that's a chiral source for this 1,3 dipolar cycloaddition reaction. And now you can see there are 3 chiral centers which are fixed during this 1,3 dipolar cycloaddition. That is because of this external chiral ligand. Okay. Then this NN bond can be cleaved. Already we discussed when we talked about nitrones in 1,3 dipolar cycloaddition. You have cleaved the NO bond with many reagents. Here, that NN bond also can be cleaved by treating with samarium iodide. So this is another very simple example where you have the azomethine imine and the double bond is part of the ring. Now this can undergo 1,3 dipolar cycloaddition with dimethylacetylene dicarboxylate to get this interesting bicyclic compound. Okay. So this is a very simple example, but the mechanism is quite interesting. So you have an aldehyde, and then this NH2 first forms the imine, then an intramolecular essential reaction, you will get this azomethane imine, and you have a double bond which will act as the dichlorophyll, and this can undergo an intramolecular 1,3 dipolar cycloaddition to get this tricyclic compound. So all this in one part. Okay, basically you take an aldehyde and then add this benzyl hydrazine and then reflex it. So in situ it forms this azomethane imine and also undergoes subsequently 1,3 dipolar cycloaddition with the double bond. So this is another classical example where you have you started with an aldehyde and then made this tosyl hydrazone. It also has a triple bond. Now when you add bromine, so what happens first? It will form the bromonium ion. Now the lone pair on the nitrogen here will attack and open this bromine. So what you get is this compound after loss of proton. So now this is a dipole, the azomethane imine, that can in principle undergo 1,3 dipolar cycloaddition with various dipoles. And for example, this can undergo 1,3 dipolar cycloaddition with ethyl acrylate to form this pyrazole derivative. Okay, this is not the direct product. First, it will form so first you will get this compound. Okay, so then the tosyl group will be eliminated So you get a double bond there, and then followed by air oxidation, you will get the corresponding reactions. Okay, so here you have a 5-membered compound. This is lactam, this is secondary amine. So when you treat this with aldehyde, only this amine will react, and that is where you see the formation of iminium ion, and this NH can be easily deprotonated, so you get this azomethine imine, and that can undergo 1,3-dipolar cycloaddition with various dipolar phials, and here it reacts with dimethyl dicarboxylate to give this bicyclic compound, and it reacts with methyl acrylate to give this bicyclic compound, and here in this case it reacts with the dimethyl meliate to give this bicyclic compound. So in this case, if you see, there are 5 chiral centers, okay, and these 5 chiral centers are fixed by the existing 2 chiral centers. Okay, one can also think about intramolecular 1,3-dipolar cycloaddition. For example, you have aldehyde and then treat with this 5-membered compound, so it can form the azomethane imine, and once it forms, then it can undergo intramolecular 1,3-dipolar cycloaddition to give this bicyclic compound. All this in one step. You have aldehyde and hydrogen derivative. Okay, mix these two. Either you have to heat it, or sometimes this can undergo intramolecular 1,3-dipolar cycloaddition at even room temperature. Okay, and this is another classical example. So if you take styrene and then treat with this dipole, in principle it can undergo 1,3-dipolar cycloaddition to form this compound. And now if you look at this particular intermediate, you can see it can undergo an extrusion of carbon dioxide. When the extrusion of carbon dioxide takes place, this is what you will get. Okay, so then it can undergo easily tautomization to give this bond. Okay, so now we'll move to the last dipole. So that is nothing but nitrile ylides. Okay, so we know nitriles, and next to nitrile, if you have a carbon bearing negative charge, then this is called nitrile ylide. So this portion is nitrile, and the nitrogen has a positive charge, and the carbon which is attached to nitrogen, if it has a negative charge, so this is called nitrile ylides. So these nitrile ylides can be prepared by 3-4 methods. For example, if you have this as C double bond O, then carbon dioxide elimination can give this nitrile ylide, or if you have this as nitrogen, then exclusion of nitrogen, removal of nitrogen can give this nitrile ylide, or if you have a nitrile and then if you treat with a carbene, okay, then the lone pair on the nitrogen can attack the carbene to form the nitrile ylide, or one can also take the azridine and then break this bond to get corresponding nitrile ylide. Sorry, you have to break this bond. Last option is if you have an imine having a leaving group at alpha position. Now, if you treat with base, so first nitrile will form, then followed by integration of anion, one can make nitrile ylides. So these nitrile ylides, like other dipoles, can undergo 1,3-dipolar cycloaddition, and here this is the major product, and this type of nitrile ylides, as I said, you can easily prepare by mixing a nitrile and the diazole compound in the presence of copper or rhodium catalyst to generate this nitrile ylide in situ, and once you have that, this can undergo 1,3-dipolar cycloaddition with various dipolar phial. For example, it can undergo 1,3-dipolar cycloaddition with the diazole compound to give this triazoles. One can also make pyrols using 1,3-dipolar cycloaddition between nitrile ylide and dimethyl acetylene dicarboxylate or any alkyne. Okay, so this nitrile ylide, when you do a 1,3-dipolar cycloaddition with dimethyl acetylene dicarboxylate, it can undergo 1,3-dipole cycloaddition. Now, this can, in principle, undergo 1,5-hydrogen shift to give the tetra-substituted pyrroles. So, what we have discussed today is the utility of 4 different dipoles in 1,3-dipole cycloaddition, and so far in the last 6 lectures, we have discussed in details of various 1,3-dipoles being used in 1,3-dipole cycloaddition reaction. Okay, we will stop here, and from next class onwards, we will talk about 2+2 cycloaddition, and also in the last lecture, we will talk about molecular orbital correlation of 4+2, 3+2, and 2+2 cycloaddition reaction. Okay, thank you.